Hello, welcome to another module in this massive open online course, Principles of CDMA, MIMO, OFDM wireless communication systems. And what we are going to do today in this module is to basically go through the evaluation of the exact bit rate expression for a wireless communication system. Remember, in the previous module, we had stopped short of the complete derivation. What we said was we have to evaluate the average this bit rate expression q of square root of a square times SNR with respect to the distribution of the amplitude of the fading channel coefficient A, that is given by the Rayleigh density 2a e power minus a square. So, this integral, that is the average bit rate, this we had gone through the derivation of this to derive the final expression in the previous module. So, that is something that we are going to do in the module today, that is to evaluate the exact expression for the bit error rate. So, we are going to derive exact bit error rate expression for a or of a exact bit error rate expression for a wireless communication system. And we have already seen that the average bit error rate is given as the integral 0 to infinity q of square root of a square SNR times 2a e to the power of minus a square dA. Now, what we are going to do is we are going to substitute this SNR by the symbol mu, and therefore, I can write this quantity as 0 to infinity q of square root of a square times mu 2a e to the power of minus a square dA. And now, we know that the expression for the q function, we know that q of v equals integral v to infinity 1 over square root of 2 pi e raised to minus t square by 2 dt, that is q of v for the argument v is given as integral v to infinity 1 over square root of 2 pi e raised to minus t square by 2 dt. If I substitute that q function here, I will get the bit error rate equals basically 0 to infinity square root of a square mu to infinity 1 over square root of 2 pi e to the power of minus t square by 2 dt times 2a e to the power of minus a square d 2 to the power of minus a square dA, where this inner integral, if you look at it, this inner integral is with respect to t, and the outer integral is with respect to the quantity a, right. So, this is a double integral, the inner integral is with respect to the quantity t, outer integral is with respect to the amplitude of the fading channel coefficient a. Now, I am going to use the substitution t divided by a square root of mu equals u, which also gives me d of t equals a square root of mu times d of u. Therefore, substituting this, my bit error rate expression now reduces to integral 0 to infinity. If when t is equal to a square root of mu, u is equal to t divided by a square root of mu, that is a square root of mu divided by a square root of mu. So, the t u is equal to 1. When t is equal to infinity, t divided by a square root of mu is also infinity. So, therefore, the integral limits are now changed to 1 to infinity 1 divided by square root of 2 pi e raised to minus, now t is u a square root of mu. So, this is minus u square a square mu divided by 2 times, now we have dt, dt is a square root of mu times du times 2a e raised to minus a square dA. So, now I have this modification using the substitution t divided by a square root of mu is equal to u. I have this modified double integral. Now, I am going to have, I have two terms with minus with a square in the exponent. I am going to combine these two terms as bit error rate or the average bit error rate is equal to I am going to bring square root of mu out, square root of mu if I bring out 0 to infinity 1 to infinity 2a square by square root of 2 pi times e raised to minus a square divided by 2 plus mu u square times dA times dA times du times dA. And now, what I am going to do is further, what I am going to do now is I am going to change the order of these two integrals. Remember here, if you look at this, I have the inner integral with respect to u and the outer integral with respect to a. I am going to change the order of these integrals, and therefore, now what I am going to have is I am going to bring the integral with respect to u outside. I am going to take the integral with respect to a inside. I have 2a square divided by square root of 2 pi e raised to minus a square by 2 plus mu u square dA d mu, and now therefore, I have the inner integral with respect to a and I have the outer integral with respect to mu. Okay. Right. So, now I have the double integral, I have changed the order of the reverse the order of integration. So, I have the inner integral with respect to a and the outer integral with respect to u, correct. And now, what I am going to do is I am going to first evaluate the inner integral. I am going to evaluate the inner integral, which is basically 2a square divided by square root of 2 pi e to the power of minus a square by 2 times 2 plus mu u square dA from 0 to infinity. Now, if you look at this, let us look at the following result. For a Gaussian, we have the following result. For a Gaussian distribution, we have t square divided by 2 pi sigma square integral minus infinity to infinity e raised to minus t square divided by 2 sigma square dt. Now, this quantity, this is simply an evaluation of the variance of the Gaussian distribution of the 0 mean Gaussian random variable with mean 0 and variance sigma square. So, therefore, this is equal to sigma square. And now, you look at this, this is integral involves t square. So, it is symmetric for minus t and that is for negative values and positive values. So, this implies this is twice the integral 0 to infinity t square divided by square root of 2 pi, bring the sigma out e raised to minus t square divided by 2 sigma square dt equals sigma square. And now, this sigma is a constant. So, I can move it from the denominator on the left to the right, and therefore, I will have integral 0 to infinity 2 t square divided by square root of 2 pi e raised to minus t square divided by 2 sigma square dt equals sigma cube. And therefore, this is the result I am going to now employ to simplify. Now, look at this, I have an integral 2 a square divided by square root of 2 pi e raised to minus a square by 2, And if you look at compare these two integrals, you can see the integral on the top is equal to the integral on the bottom. All I have to do is I have to substitute sigma square equals basically 1 over 2 plus mu u square, or basically what we have is 1 over sigma square equals 2 plus mu u square. Therefore, this integral is equal to sigma cube which is equal to 1 over 2 plus mu u square raised to the power of 3 by 2. So, therefore, inner integral with respect to A is equal to 1 over 2 plus mu u square raised to the power of 3 by 2, that is the inner integral with respect to A. Now, let us evaluate the outer integral with respect to u. So, now I have bit error rate is given by the outer integral which is integral 1 to infinity square root of mu times 1 over 2 plus mu u square raised to the power of 3 by 2 du, and now I am going to use the substitution u is equal to square root of 2 by mu tan of theta. Now, therefore, when u equals 1, I have theta equals tan inverse square root of mu by 2. When u equals infinity, theta is equal to tan inverse infinity equals pi by 2. So, the limits of this integral become, this is an integral from tan inverse square root of mu by 2 to pi by 2 of 1 over, now I am going to substitute u equals square root of 2 over mu tan theta, which when I substitute this it becomes 2 plus mu u square, which becomes 2 plus twice tan square theta raised to the power of 3 by 2. Also, you can see from here, if du is equal to square root of 2 by mu tan theta, then du is equal to square root of 2 by mu secant square theta d theta. So, I am going to write this as square root of 2 by mu secant square theta d theta. And now, when I simplify this integral, I have this bit error rate is basically equal to square root of mu tan inverse square root of mu over 2 to pi by 2 1 over 2 plus 2 tan square theta 3 by 2 raised to the power of 3 by 2 by mu square root of 2 by mu secant square theta d theta, and now you can see the square root of mu cancels, and therefore, what I have is tan inverse square root of mu by 2 to the power of to pi by 2 square root of 2 divided by 2 raised to 3 by 2 times 1 over secant cube theta times secant square theta d theta, which is equal to half. Now, secant square theta in the numerator, secant cube theta in the denominator, that cancels, and what will remain is 1 over secant theta, which is nothing but cosine of theta. So, it is half integral from tan inverse mu over 2 to pi by 2 cosine of theta d theta, but integral of cosine of theta is sin theta. So, this is half of sine of theta evaluated between the limits tan inverse square root of mu over 2 to pi by 2, and therefore, what I will get is now bit error rate is equal to half sine of pi by 2, which is 1, minus sine of tan inverse of square root of mu divided by 2. Now, we are going to use the identity, we are going to use a trigonometric identity, that is sine of theta equals square root of tan square of theta divided by 1 plus tan square of theta. Therefore, sine of tan inverse square root of mu by 2 is equal to square root of tan square of is equal to square root of tan square of tan inverse square root of mu by 2 divided by 1 plus tan square of tan inverse square root of mu by 2, which is equal to square root of tan inverse mu by square root of mu by 2 is simply mu by 2 divided by 1 plus mu by 2, which is nothing but square root of mu divided by 2 plus mu, and remember our mu is nothing but a substitution for SNR. Therefore, the average bit error rate is now substituting mu is equal to substituting back mu is equal to SNR, I get the bit error rate equals half 1 minus square root of SNR divided by 2 over SNR. And if you remember, this is the exact expression that we had previously, that is the average bit error rate is half 1 minus square root of SNR divided by 2 plus SNR. Therefore, what we have done is now we have evaluated this integral, we have gone through the detailed derivation of this bit error rate expression to derive the relation that the bit error rate in a wireless communication system, the average bit error rate, which is average with respect to the distribution of the amplitude of the fading channel coefficient A, is given as half times 1 minus square root of SNR over 2 plus SNR. Therefore, our bit error rate in the wireless communication system is half times 1 minus square root of SNR divided by the bit error rate of the wireless communication system is half square root 1 minus square root of SNR divided by 2 plus SNR. This is the expression for the bit error rate, this is the expression for the average bit error rate. Mind you, this is the average bit error rate. Bit error rate for BPSK transmission in Rayleigh fading. The nature of the fading is also important. Rayleigh fading wireless, this is the average bit error rate. This is the formula for the average bit error rate for BPSK modulation in a Rayleigh fading wireless channel. And what we have done is we have derived the exact expression for this bit error rate. So, this module, we will stop this module here and we will continue with other topics in the subsequent modules. Thank you very much.